using polyvinyl chloride, often shortened to PVC conduit for high-voltage electrical installations, particularly at 15 kilovolts and in environments like boiler rooms, raises substantial safety concerns. PVC, while a versatile and cost-effective material for many electrical applications, possesses inherent limitations that make it unsuitable for high-voltage systems. Firstly, PVC dielectric strength, which is its ability to withstand electrical stress without breaking down, is significantly lower compared to other conduit materials like steel or aluminum. This lower dielectric strength means that PVC is more susceptible to electrical breakdown when exposed to high voltages. A breakdown can lead to arcing, which is the formation of an electrical discharge through the air or along the surface of the conduit. Arcing poses a serious fire hazard, as it can ignite flammable materials in the vicinity. Secondly, PVC is more prone to degradation when exposed to high temperatures. Boiler rooms are typically characterized by elevated temperatures due to the operation of boilers and related equipment. The increased heat can soften PVC, reduce its structural integrity, and making it more vulnerable to physical damage. This softening can also compromise the conduit's ability to contain and protect the high-voltage conductors. Thirdly, PVC is a combustible material, meaning it can catch fire and burn. While PVC is often treated with flame retardants to slow down the spread of fire, it will still burn under intense heat. In the event of an electrical fault or fire, the burning PVC can release toxic fumes, posing a health hazard to anyone in the area. Fourthly, the National Electrical Code, often referred to as NEC, provides specific guidelines for the installation of electrical systems, including conduit types and their approved uses. While the NEC does not explicitly prohibit the use of PVC for all high-voltage applications, it emphasizes the need for proper engineering supervision and adherence to safety standards. The NEC also requires that all electrical installations be suitable for their intended use and environment. Given the potential safety hazards associated with using PVC in high-voltage and high-temperature environments, it is generally not recommended. It is crucial to consult with qualified electrical engineers and adhere to the NEC guidelines to ensure the safety and reliability of electrical installations. Fifthly, the grounding of electrical systems is critical for safety. In high-voltage systems, proper grounding helps to prevent electrical shock hazards and minimizes the risk of equipment damage. When using PVC conduit, it is essential to ensure that the grounding conductors are properly installed and bonded to the electrical equipment. Since PVC is a non-conductive material, it cannot provide a grounding path. Therefore, a separate grounding conductor must be run inside the conduit to provide a reliable grounding path. Sixthly, the selection of conduit size is also important for high-voltage applications. The conduit must be large enough to accommodate the conductors and provide adequate space for heat dissipation. Overcrowded conduits can lead to overheating, which can degrade the insulation of the conductors and increase the risk of electrical faults. Seventhly, when installing conduit in a surface-mounted configuration, it is essential to ensure that the conduit is properly supported and secured. This helps to prevent the conduit from sagging or becoming damaged. Surface-mounted conduit is more vulnerable to physical damage than conduit that is buried or concealed. Therefore, it is important to protect the conduit from impact and abrasion. Eighthly, the use of proper fittings and connectors is also crucial for ensuring the integrity of the conduit system. Fittings and connectors must be compatible with the conduit material and rated for the voltage and current levels of the electrical system. Improper fittings and connectors can lead to loose connections, which can cause arcing and overheating. Ninthly, regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. High-voltage systems should be inspected regularly for signs of damage, wear, or corrosion. Any damaged or worn component should be replaced promptly. Tenthly, it is important to consider the potential for induced voltages in high-voltage systems. Induced voltages can occur when conductors are run in close proximity to each other. These induced voltages can pose a shock hazard and can also interfere with the operation of sensitive electronic equipment. To minimize the risk of induced voltages, it is important to maintain adequate separation between conductors and to use shielded cables. 11thly, surge protection devices can help to protect electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, switching operations, or other electrical disturbances. Surge protection devices can divert the surge current away from the equipment, preventing damage. 12thly, proper labeling and signage are essential for identifying high voltage equipment and warning personnel of potential hazards. High voltage equipment should be clearly labeled with appropriate warning signs. 13thly, training and qualification are essential for personnel who work on high voltage electrical systems. Personnel should be properly trained in the safe operation and maintenance of high voltage equipment. They should also be familiar with the relevant safety standards and regulations. 14thly, the NEC Table 310.15b16 provides ampacity ratings for conductors based on insulation type and temperature rating. When selecting conductors for high voltage applications, it is important to choose conductors with an appropriate ampacity rating for the expected current load. 15thly, the NEC Article 300 covers general requirements for wiring methods and materials. This article includes provisions for conduit fill, conductor bending radius, and support requirements. 16thly, the NEC Article 310 covers conductors for general wiring. This article includes provisions for conductor insulation types, ampacity ratings, and dirting factors. 17thly, the NEC Article 392 covers cable trays. Cable trays are often used to support high voltage cables in industrial and commercial applications. 18thly, the NEC Article 490 covers equipment over 600 volts nominal. This article includes provisions for high voltage switchgear, transformers, and other equipment. 19thly, consider using rigid metal conduit, often shortened to RMC, instead of PVC for high voltage applications. RMC provides superior mechanical protection and is less susceptible to damage from heat and impact. 20thly, if RMC is not suitable, consider using intermediate metal conduit, often shortened to IMC. IMC is lighter than RMC but still provides good mechanical protection. 21st, another alternative is to use electrical metallic tubing, often shortened to EMT. EMT is a thin-walled conduit that is suitable for use in dry locations. 22nd, consider using liquid-type flexible metal conduit, often shortened to LFMC, for short runs where flexibility is required. LFMC provides a flexible connection while still providing good mechanical protection. 23rd, always consult with a qualified electrical engineer or electrician to determine the most appropriate wiring method for your specific application. They can assess the specific risks and requirements and recommend a solution that meets all applicable safety standards. 24th, it is important to remember that electrical codes and standards are constantly evolving. Stay up to date on the latest requirements to ensure that your electrical installations are safe and compliant. 25th, consider the long-term cost of the installation. While PVC may be less expensive upfront, the cost of replacing damaged or degraded PVC conduit can be significant over time. 26th, consider the environmental impact of the materials you are using. PVC is a plastic material that is not easily recycled. Consider using more sustainable materials whenever possible. 27th, remember that safety is always the top priority. Never compromise safety for cost or convenience. 28th, proper planning and design are essential for ensuring the safety and reliability of electrical installations. Take the time to carefully plan your installation and ensure that all components are properly selected and installed. 29th, always follow the manufacturer's instructions for installing and using electrical equipment. The manufacturer's instructions provide important safety information and guidance on proper installation techniques. 30th, consider using a ground fault circuit interrupter, often shortened to GFCI, to protect personnel from electrical shock hazards. A GFCI will detect ground faults and quickly interrupt the circuit, preventing serious injury. 31st, consider using an arc-fault circuit interrupter, often shortened to a PSI, to protect against electrical fires. An PSI will detect arc faults and quickly interrupt the circuit, preventing a fire from starting. 32nd, consider using a surge protective device, often shortened to SPD, to protect electrical equipment from damage caused by voltage surges. An SPD will divert the surge current away from the equipment, preventing damage. 33rd, consider using a voltage monitoring device to monitor the voltage levels in the electrical system. A voltage monitoring device can detect voltage fluctuations and alert personnel to potential problems. 34th, consider using a current monitoring device to monitor the current levels in the electrical system. A current monitoring device can detect overloads and short circuits and alert personnel to potential problems. 35th, consider using a temperature monitoring device to monitor the temperature of electrical equipment. A temperature monitoring device can detect overheating and alert personnel to potential problems. 36th, consider using a vibration monitoring device to monitor the vibration levels of electrical equipment. A vibration monitoring device can detect imbalances and mechanical problems and alert personnel to potential problems. 37th, consider using a power quality analyzer to analyze the power quality in the electrical system. A power quality analyzer can detect voltage sags, voltage swells, harmonics, and other power quality problems. 38th, consider using a thermal imaging camera to inspect electrical equipment for hot spots. A thermal imaging camera can detect overheating and potential problems. 39. Consider using an ultrasonic leak detector to detect leaks in compressed air or gas systems. An ultrasonic leak detector can detect leaks that are not audible to the human ear. 40th, consider using a combustible gas detector to detect the presence of combustible gases. A combustible gas detector can detect leaks and prevent explosions.